The most popular soda flavors are engineered products built at massive scale. From precise syrup blending to high-speed bottling lines, each soda follows a tightly controlled process that transforms simple ingredients into globally recognized flavors. Today, we go inside the factories to see how Fanta Grape gets its bold taste, how Pepsi maintains consistency worldwide, and how Sprite achieves its iconic fizz. Grape flavor for Fanta is created by combining a concentrated blend of esters and aldehydes in a stainless steel mixing tank. Each flavor compound is pre-measured using peristaltic pumps connected to sealed containers. The mixer runs at low speed to avoid aeration while ensuring even distribution. Glycol-based carriers are added to solubilize the aromatic compounds. Food-grade purple pigment is introduced through a high-shear inline mixer. Color density is verified using optical sensors positioned on the outflow pipe. Malic acid is dosed through a diaphragm pump to set target acidity. Potassium citrate is used to buffer pH and stabilize the flavor profile during dilution. The flavored concentrate is transferred to a holding tank through a closed-loop circuit. This circuit is jacketed for temperature stability using chilled glycol at 5 degrees Celsius. Once the concentrate is blended, it waits for combination with sweeteners and water during syrup preparation. In a separate process, sucrose and high fructose corn syrup are stored in heated silos connected to the syrup room. Each is pumped into the blending vessel using independent flow meters. Ratios are defined by weight and adjusted by mass flow controllers. Purified water is added last and enters from a pressure-regulated manifold connected to a reverse osmosis unit. The water temperature is maintained at 25 degrees Celsius to optimize mixing of sugars. This solution forms the neutral base syrup, which will be used in the final product. Blending occurs in a high-capacity horizontal tank fitted with two counter-rotating paddles. The sweetener solution is mixed for 5 minutes before receiving the flavored concentrate. Both streams are combined through a Y junction with a static mixer installed in line. As soon as the base and flavor are unified, a light degassing takes place using a vacuum chamber positioned before the storage tank. This step removes trapped air introduced during transfer or agitation. Once degassed, the finished syrup is cooled to 4 degrees Celsius through a tubular heat exchanger before entering carbonation. Carbon dioxide is stored in a bulk tank under pressure and delivered to the carbonation chamber through flow-restricted piping. Syrup enters the carbonator at a controlled rate using a servo-actuated pump. Gas is dissolved by injecting microbubbles into the moving syrup using sintered metal diffusers. Carbonated syrup exits into a buffer tank positioned above the filler. This tank maintains constant head pressure to stabilize flow. The syrup in this tank is kept cold by recirculating chilled water around the vessel jacket. A level sensor manages inflow from the carbonator to prevent overflow. PT bottles are formed on site, starting with preforms loaded into a hopper. Each preform is picked by a rotary arm and placed into a mold. Stretch blow molding begins with heating preforms to 110 degrees Celsius using infrared lamps. Heated preforms are stretched vertically, then expanded with high-pressure air into bottle shape. The finished bottles are transferred by neck holders to the rinsing carousel. A nozzle enters each bottle and injects sterile water to remove particulates. Rinsed bottles move to the filler via a star wheel which positions each neck under a filling valve. The filling machine is isobaric, which keeps bottle pressure equal to syrup pressure. Each filling valve opens when the bottle rises and seals against the valve head. Syrup flows into the bottle until it reaches a fill height, set by vent tubes inside the filler. Filled bottles move to the capping unit by synchronized belts. Caps are fed from a hopper by centrifugal sorter and aligned onto the bottle mouths. A chuck lowers to apply torque and twist the cap until threads lock. Capped bottles exit the machine and pass under a sensor that checks cap presence. From there, bottles enter a labeler which wraps shrink film labels around each one. Steam is applied at the next station to shrink the label tightly to the bottle contour. Each labeled bottle proceeds to the date coding unit, which uses inkjet technology to print production time and batch ID. The code is placed near the bottleneck on a dry area for visibility. Bottles are arranged into rows on a conveyor, where a grouping arm places them into crates. The crates move to a palletizer, which builds vertical stacks using a programmed layer pattern. Full pallets are wrapped with plastic film and moved to storage. Multiple syrup batches are prepared per shift to meet production demand. Each flavor concentrate batch can serve hundreds of liters of syrup. Flavor components are blended using programmable dosing, which adjusts for differences in raw material concentration. Sweeteners are kept warm to maintain viscosity within pumping range. Pipes carrying syrup and concentrate are inclined to assist gravity drainage between batches. At the end of a run, residual syrup is pushed from the line using a slug of water. No manual steps are required between blending and packaging. Each process is actuated by a control system that receives sensor input in real time. Syrup density is confirmed by inline refractometers, which monitor sugar concentration continuously. CO2 solubility is affected by temperature and pressure, so both are monitored at the carbonation point. If syrup warms or pressure drops, gas volume per litre decreases, which affects final mouthfeel. The carbonator compensates by adjusting dwell time or increasing gas injection rate. Bottle fill height is controlled by vacuum venting, which halts flow when liquid touches the vent tube. Changes in bottle wall thickness can cause variation, so backup cameras verify level post-fill. Cap torque is adjusted per cap type and plastic grade to ensure no leaks during storage. Chucks are recalibrated weekly to stay within set force range. Labels are applied with 2 rollers that press opposing edges for full wrap. Label overlap is held with heat-activated adhesive. Preform quality affects bottle strength and clarity. Each batch of preforms is scanned with laser sensors before molding to detect warping or occlusions. Mold temperature is kept constant by circulating oil at 130 degrees Celsius to avoid visual defects. Steam tunnels that shrink labels are fed from an external generator with PID temperature control. Excess steam is extracted by hood fans that channel it to condensers. Label seam alignment is guided by photoelectric sensors that track the mark on the film roll. Filled bottles move at a constant speed, so all label, code, and grouping systems stay in sync. Synchronization is achieved by encoders mounted on main drive shafts which share position data with subsystems. Each syrup blend is traced by batch number from ingredient addition to final packaging. Although this data is recorded, it is not part of the physical process. Blending tanks are equipped with magnetic agitators that mix syrup without shaft penetration. Flavor consistency depends on the timing of concentrate addition and mix speed. The flavor tank uses baffles to prevent vortexing, which could pull air into the blend. Air entrapment can dull flavor strength or reduce CO2 absorption. Grape flavor components include methyl anthranilate and esters, which require uniform dispersion. These are added to the aqueous base in small volume, but have strong impact on profile. Capping speed is linked to fill rate, so as syrup flow increases, the capping turret rotates faster. Caps are pressed with fixed downward force and twisted with servo torque control to prevent over-tightening. Once filled and wrapped, bottles are moved in grouped rows onto collection belts. These belts advance the product toward pallet stations based on sensor feedback. No bottle moves backward once it enters the filling zone. Pepsi manufacturing begins with bulk water intake as the dominant material by mass. Incoming water is routed through coarse mechanical strainers that remove visible solids. The water then moves through layered depth filters that trap suspended particulates by pore restriction. Clarified water enters activated carbon columns where organic molecules bind to the carbon surface. This stage removes odor, causing compounds and trace oxidants. The water is then pushed through reverse osmosis membranes using high-pressure pumps. Ionic species and dissolved minerals are rejected by the membrane structure. The permeate stream exits with tightly controlled conductivity. This purified water is collected in stainless holding tanks with automated level regulation. Temperature conditioning systems adjust the water to a cold range suitable for carbonation efficiency. Sweetener handling begins separately from water preparation. High fructose corn syrup arrives as a viscous liquid stored in heated tanks. Internal recirculation loops prevent phase separation and crystallization. The syrup is metered using positive displacement pumps. Flow meters verify mass accuracy in real time. The syrup line connects to a blending manifold with automated valves. Concentrated flavor base is stored in sealed containers under controlled conditions. The flavor concentrate is dosed in extremely small volumes relative to water. Precision pumps inject the concentrate into the syrup stream. Acid components are added through independent dosing lines. Caffeine is introduced in dissolved form to ensure uniform distribution. Blending occurs inside large agitated mix tanks. Water enters first to establish dilution volume. Syrup follows at a calibrated ratio defined by formulation parameters. Flavor concentrate is injected downstream of the syrup entry point. High-speed impellers generate turbulent flow patterns. This turbulence ensures molecular level mixing of all components. Inline refractometers measure sugar concentration continuously. pH probes monitor acidity throughout the blend cycle. Control systems adjust flow rates dynamically to correct deviation. The completed liquid at this stage is uncarbonated Pepsi base. Carbonation preparation requires cooling before gas injection. The blended liquid passes through plate heat exchangers. Refrigeration circuits lower the temperature close to freezing. Cold liquid improves carbon dioxide solubility. The chilled beverage enters a pressurized carbonation vessel. Carbon dioxide is injected through fine pore diffusers. Gas disperses as microscopic bubbles within the liquid. Tank pressure is elevated to force dissolution. Sensors measure dissolved CO2 concentration continuously. Agitation is minimized to prevent gas loss. The fully carbonated Pepsi is held under pressure until packaging. Container production may occur in line for plastic bottles. PET preforms are loaded into infrared heating ovens. Rotating spindles expose the preforms evenly to heat. The softened preforms transfer into blow molding stations. High pressure air expands the material inside metal molds. The bottle shape forms instantly against the mold walls. Cooling channels solidify the plastic rapidly. Finished bottles exit onto air conveyors. These conveyors suspend bottles by their neck rings. The bottles travel directly to the filling area. Empty bottles enter a rinsing carousel. Jets of filtered air remove dust and debris. Bottles are inverted during this process. They then move into the rotary filling machine. Each bottle engages a filling valve. Carbonated Pepsi flows under controlled pressure. Fill height is determined by internal tube length. Foam generation is minimized through pressure equalization. Filled bottles rotate out of the filler. Excess liquid is returned to the system. Capping occurs immediately after filling. Caps are sorted using centrifugal orientation systems. Properly aligned caps slide down chutes to the capping heads. Each head lowers a cap onto a bottle neck. Torque controlled spindles tighten the closure to specification. Seal integrity depends on precise compression of the liner. Improperly sealed bottles are detected by inspection sensors. Rejected units are removed from the line automatically. After sealing bottles pass through inversion belts. This allows liquid contact with the cap liner. The contact helps maintain internal cleanliness. Bottles return upright and continue forward. Labeling follows next in sequence. Bottles are synchronized with rotating label drums. Labels are applied using adhesive or heat shrink methods. Registration systems align graphics precisely. Optical scanners verify placement accuracy. Misaligned labels trigger rejection mechanisms. Date coding is applied using non-contact printers. Inkjet nozzles deposit characters onto the bottle surface. Codes include production time and batch reference. Ink is dried instantly using directed air. Bottles proceed toward packaging zones. Grouping conveyors accumulate bottles into fixed counts. Mechanical gates release bottles into pack formation. Shrink film is dispensed over each group. Heat tunnels shrink the film tightly around the bottles. Temperature zones ensure even contraction. Wrapped bundles transfer to palletizing systems. Layers are arranged according to predefined patterns. Robotic arms position bundles with high repeatability. Slip sheets may be inserted between layers. Pallets are built vertically with controlled alignment. Completed pallets enter stretch wrapping machines. Film is stretched and wrapped around the load. Rotational platforms ensure full coverage. Wrapped pallets exit towards storage dispatch. Production follows a parallel, but distinct path. Aluminum coil stock is unrolled continuously. Lubrication reduces friction during forming. Blanking presses punch circular discs from the sheet. These discs are drawn into shallow cups. Redraw and ironing stages elongate the cups. Wall thickness is reduced to precise tolerances. The base is domed for pressure resistance. Trim cutters remove excess material from the rim. Cans undergo washing after forming. Chemical sprays remove oils and residue. Rinsing stages follow to eliminate cleaning agents. Interior coating is applied by spray nozzles. Epoxy liner coats the internal surface. Ovens cure the liner through controlled heating. Exterior printing applies graphics in multiple layers. Each color is applied by separate rollers. Registration control ensures image alignment. A protective overcoat seals the printed surface. Necking machines reduce the top diameter gradually. Multiple stations form the final opening. This reduces lid size and material use. Finished cans are inverted for cleaning. Air and water remove remaining particles. Clean cans enter the filling line. Carbonated Pepsi is dispensed rapidly into each can. Fill volume is controlled by valve timing. Foam suppression techniques maintain accuracy. Immediately after filling lids are applied, aluminum ends are placed on each can. Seamers fold the lid onto the can flange. Double seams are formed through roller pressure. Seam geometry determines seal strength. Inline inspection systems measure seam dimensions. Defective seams are rejected automatically. Filled cans proceed to stabilization conveyors. Gentle vibration equalizes internal pressure. Cans receive date codes next. Inkjet systems mark the base or sidewall. Codes dry instantly without contact. Cans are grouped into multi-pack formats. Collation systems align cans into rows. Paperboard or plastic carriers are applied. Packs move into secondary packaging equipment. Corrugated cases are erected automatically. Packs are inserted into cases. Glue systems seal the case flaps. Cases are stacked onto pallets by robotic systems. Layer patterns optimize stability and space. Pallets are wrapped with stretch film. Barcode labels are applied for tracking. Pallets move to finished goods zones. Throughout Pepsi production, all machines operate under synchronized control. Programmable logic controllers manage timing and coordination. Sensors provide constant feedback on flow and pressure. Recipes define exact ratios and conditions. Automated valves direct fluids precisely. changeovers adjust machine geometry without manual intervention. Buffer conveyors absorb speed differences. This maintains continuous operation across the line. Cleaning cycles run between production runs. Internal piping is flushed with cleaning solutions. Rinsing restores the system to production readiness. All tanks and lines return to a neutral state. The next batch begins with identical parameters. The manufacture of Sprite begins with water as the dominant material stream entering the production system. Incoming water flows through intake valves into primary clarification units. Large particulate matter is removed through mechanical screening using fixed aperture grids. The water then enters depth filtration vessels filled with graded media. Suspended solids are captured through physical entrapment. The clarified water passes into activated carbon beds. Organic compounds bind to the carbon surface through adsorption. Residual oxidants are removed at this stage. The water proceeds into reverse osmosis modules driven by high-pressure pumps. Semi-permeable membranes separate dissolved minerals from the permeate stream. Reject water exits the system while purified water continues forward. Conductivity sensors verify mineral removal accuracy. The purified water is stored in stainless reservoirs. Automated level controls regulate supply to downstream processes. Heat exchangers adjust water temperature to a chilled range. Cooling improves later gas absorption performance. Sweetener preparation occurs in a parallel system isolated from water treatment. Liquid sugar syrup is stored in jacketed tanks. Thermal jackets maintain viscosity within pumpable limits. Internal circulation loops prevent stratification. Syrup exits storage through positive displacement pumps. Flow is regulated using mass flow controllers. The syrup line includes inline strainers to remove insoluble particles. The sweetener stream enters a blending manifold. Concentrated lemon-lime flavor base is introduced through micro-dosing pumps. The flavor base is highly concentrated and added in minimal volume. Acid components are injected separately to control final acidity. Citric acid solution enters through metered valves. Sodium-based modifiers may be added to balance taste profile. Caffeine is not included in the formulation. All liquid ingredients converge at a controlled junction point. Mixing occurs inside large stainless blend tanks. Purified water enters first to establish volume. Sweetener follows at a precise ratio. Flavor and acid streams are injected sequentially. High-speed impellers rotate within the tank. Turbulent flow patterns eliminate concentration gradients. Mixing energy is controlled through variable frequency drives. Inline sensors monitor dissolved solids continuously. Brix values are calculated in real time. pH probes track acidity throughout the blend. Control systems adjust ingredient flow automatically. The resulting liquid is a non-carbonated Sprite base. This base is transferred through sealed piping. Pumps maintain steady flow without introducing air. The blended liquid must be cooled before carbonation. Plate heat exchangers remove thermal energy. Refrigeration circuits lower temperature near freezing. Cold liquid improves carbon dioxide solubility. The chilled beverage enters a carbonation vessel. Carbon dioxide gas is supplied from bulk storage. Gas passes through pressure regulators. Before injection, diffusers at the vessel base release gas as fine bubbles. Pressure inside the vessel is elevated. Gas dissolves into the liquid under compression. Dissolved CO2 concentration is measured continuously. Feedback loops regulate gas flow precisely. Agitation is minimal to prevent gas escape. Carbonated Sprite is held under pressure until filling. Plastic bottle production may occur in line with filling operations. PET preforms are delivered to heating systems. Infrared lamps heat the preforms uniformly. Rotating spindles ensure even temperature distribution. Heated preforms enter blow molding stations. High pressure air stretches the material axially and radially. Mold cavities define final bottle geometry. Cooling channels extract heat rapidly. The solidified bottles exit the molds. Neck rings support bottles on air conveyors. Directed airflow moves bottles toward filling. Mechanical contact is minimized to preserve shape. Empty bottles enter a rinsing carousel. Inverted orientation allows debris removal. Filtered air or treated water flushes the interior. Bottles rotate through the system rapidly. Clean bottles exit upright. They move directly into the filling machine. Rotary fillers synchronize bottle movement. Each bottle engages a filling valve. Carbonated Sprite flows under controlled pressure. Pressure equalization limits foam formation. Fill height is determined by vent tube geometry. Excess gas is recovered by the system. Filled bottles exit the filler smoothly. Capping follows immediately after filling. Caps are delivered in bulk to sorting equipment. Centrifugal force orients caps correctly. Oriented caps slide into feed chutes. Capping heads descend onto bottlenecks. Torque motors tighten caps to specification. Seal quality depends on liner compression. Sensors monitor applied torque continuously. Improperly sealed bottles are detected. Reject mechanisms remove faulty units. Sealed bottles pass through inversion conveyors. Temporary inversion allows liquid contact with the closure liner. Bottles return upright after inversion. They continue toward labeling stations. Labeling machines synchronize bottle rotation. Labels are applied using adhesive or heat shrink film. Servo motors control label placement precisely. Optical scanners verify label position. Barcode readability is confirmed. Misapplied labels trigger rejection gates. Date coding is applied downstream. Inkjet printers mark the bottle surface. Codes include production batch identifiers. Non-contact printing avoids surface distortion. Air knives dry the ink instantly. Bottles proceed towards secondary packaging. Accumulation tables manage flow buffering. Grouping conveyors organize bottles into fixed counts. Mechanical gates release groups simultaneously. Shrink film is dispensed over each group. Heat tunnels apply controlled thermal energy. Film contracts tightly around the bottles. Cooling zones stabilize the package. Packaged bottles move to palletizing systems. Robotic arms lift each bundle. Motion paths are pre-programmed. Bundles are arranged in defined layer patterns. Pallet platforms adjust height dynamically. Slip sheets may be inserted between layers. Completed pallets exit the palletizer. Stretch wrapping machines secure the load. Film tension is controlled precisely. Wrapped pallets receive identification labels. Barcodes link pallets to production data. Pallets move to storage or dispatch lanes. Aluminum can production follows a separate integrated process. Aluminum coils are unrolled continuously. Lubricants reduce friction during forming. Blanking presses punch discs from the sheet. Discs are drawn into shallow cups. Redraw operations increase cup height. Ironing rings thin the sidewalls. Material flows upward as thickness decreases. The base remains thicker for strength. Dome forming presses shape the bottom. Trim cutters remove excess rim material. Formed cans undergo washing. Alkaline solutions remove oils. Multiple rinse stages follow. Interior coating is applied by spray systems. Epoxy-based liner coats the interior. Curing ovens harden the coating. Exterior printing applies graphics in sequence. Each color layer is transferred by offset printing. Registration systems ensure alignment. A protective over-varnish seals the print. Printed cans pass through necking machines. Progressive dies reduce the top diameter. The final opening is formed gradually. Finished cans are inverted for cleaning. Air jets remove particles. Clean cans enter the filling line. Carbonated Sprite is dispensed rapidly. Fill valves open and close in milliseconds. Fill volume is controlled by timing. Foam management maintains accuracy. Filled cans transfer immediately to seamers. Aluminum ends are placed on each can. Rollers fold the lid onto the flange. A double seam is formed. Seam geometry determines seal integrity. Inline scanners measure seam dimensions. Defective seams are rejected automatically. Cans move through stabilization conveyors. Gentle motion equalizes internal pressure. Date coding follows using inkjet printers. Codes are applied to the can base or sidewall. Ink cures instantly. Cans are grouped into multi-pack formats. Collation systems align cans precisely. Paperboard wraps or plastic rings secure the group. Packs move to case packing equipment. Corrugated cases are erected from flat blanks. Packs are inserted into cases. Adhesive systems seal the flaps. Cases are conveyed to palletizing zones. Robotic palletizers stack cases efficiently. Layer patterns optimize stability. Pallets are wrapped with stretch film. Load integrity is verified. Identification labels are applied. Finished pallets move to outbound staging. Throughout Sprite production, all systems operate under automated control. Programmable logic controllers coordinate timing. Sensors provide constant feedback. Flow pressure and temperature are monitored. Recipes define exact proportions. Automated valves direct liquids accurately. Changeovers adjust equipment geometry automatically. Buffer conveyors absorb speed variations. Continuous operation is maintained across the line. Cleaning cycles occur between production runs. Internal pipelines are flushed. Tanks are drained and rinsed. Systems return to baseline condition. The next batch begins with identical parameters. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drinks base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a deaeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar. and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on-site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high-pressure air into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottleneck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coated, checked, and shrink-wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label, edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coating, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. In the high-output production of Coca-Cola, the process is defined by continuous motion, absolute precision, and the seamless choreography of ingredients, machines, and packaging systems that transform individual raw components into millions of finished beverages every single day. The process begins deep within the mixing facility, where highly purified water, stripped of all minerals, chemicals, and organic material through a series of activated carbon filters, deionization beds, and ultraviolet treatment chambers, forms the foundation of the beverage. This purified water, tested continuously for pH, conductivity, and microbial presence, is stored in stainless steel tanks where it awaits dosing. Simultaneously, concentrated syrup, pre-mixed to exact proportions in controlled rooms, is pumped from insulated holding tanks through jacketed pipelines that maintain a constant temperature to prevent any crystallization or viscosity shifts. These lines carry the syrup to the blending system, where the water and concentrate meet inside high-speed mixing chambers fitted with vortex turbines that spin at thousands of revolutions per minute. These turbines ensure that every drop of syrup disperses evenly throughout the water stream, achieving uniform flavor concentration at massive scale. Inline refractometers measure sugar content and density in real time, adjusting flow valves to keep the bricks level within fractions of a percent of specification. Once blended, the now recognizable but uncarbonated Coca-Cola base enters a chilling loop, where it is passed through plate heat exchangers that rapidly drop the temperature to just above freezing. This cooling is critical because carbonation requires both precision and cold liquid. Warmer temperatures reduce the solubility of carbon dioxide, and the beverage must be stabilized before the gas is introduced. The chilled liquid is then sent to the carbonation unit, a sealed pressurized chamber where CO2 is injected under precise pressure and temperature control. The carbon dioxide gas, stored in liquid form in cryogenic tanks, is vaporized and filtered before injection, ensuring purity and taste neutrality. As the CO2 is forced into the beverage under pressure, it dissolves instantly, and the resulting mixture, now fully carbonated Coca-Cola, is routed into buffer tanks, where it is gently agitated to maintain consistency and avoid foaming. These tanks are under positive pressure to prevent degassing, and every line is monitored for CO2 saturation, temperature drift, and fill levels. From these tanks, the carbonated beverage moves directly to the filling lines, which operate with unbroken efficiency, handling thousands of bottles or cans per hour with mechanical repetition and minimal tolerance for variation. For bottles, the first step begins with preforms, small plastic tubes made of PET, fed from hoppers into a rotary oven where they are heated to a malleable state, then transferred into a blow molding carousel. Inside this machine, each preform is stretched and inflated with high-pressure air into the shape of a bottle inside precision-machined metal molds. The formed bottles are immediately cooled, trimmed, and transferred onto conveyors that carry them upright toward the filling line. Throughout this path, they remain untouched by hands and isolated from ambient air by enclosed systems that maintain sanitary conditions. As they approach the filler, the bottles are inverted and rinsed internally with sterile air or ionized water to remove any particles. They then pass under the filling heads, nozzles that lower into the neck of each bottle, creating a tight seal and filling them under counter-pressure conditions to prevent foaming or CO2 loss. The entire filling cycle for each bottle takes only a few seconds, monitored by laser-level sensors that detect exact volume. As each bottle fills, the flow is throttled to avoid turbulence, and the gas pressure is equalized to maintain carbonation stability. Immediately after filling, the bottles are transferred to the capping station, where precision-guided turrets place caps onto each one and tighten them with calibrated torque drivers. The caps themselves are fed from vibratory bowls that align them correctly and move them through high-speed chutes. As each bottle is capped, it is passed through a vacuum checker that detects seal integrity by measuring internal pressure, and any container that doesn't meet the threshold is automatically diverted from the line. In parallel to bottle filling, production follows a similarly synchronized path. Aluminum cans arrive already formed, stacked, and nested, and are depalletized in towers that feed them one by one onto high-speed conveyor belts. These cans move through a rinse tunnel where jets of deionized water clean the interiors. Then dry blowers remove every drop before they reach the filler. Because cans can't be sealed under counterpressure like bottles, they are filled with a slightly different method. First purged with carbon dioxide to displace oxygen, then rapidly filled with cold, carbonated Coca-Cola, and finally topped with lids while still under pressurized gas. The lid seamer seals each can by curling the edge of the aluminum lid around the lip of the can body and compressing it tightly with a roller under immense force. The seam is inspected by cameras and load sensors, and every few hundred units, samples are removed automatically and sent to inline X-ray or cutaway analysis to ensure structural integrity. Once sealed, the cans are dried again, passed through a date coder that prints production codes and batch identifiers directly onto the lid, and then sorted into lanes based on packaging format: single, multi-pack, or bulk tray. Now fully sealed, bottles and cans alike move toward labeling and secondary packaging. Bottles pass through shrink sleeve or wraparound labelers that align each container using optical sensors before a printed film sleeve is applied and shrunk into place using steam or infrared tunnels. Can multi-packs are grouped into clusters by mechanical pusher arms and wrapped in printed film or placed into cardboard carriers. Robotic arms lift and arrange finished units into cartons or trays, depending on regional packaging standards, and automated check weighers confirm product count and configuration within each package. After secondary packaging, the products move to palletizing stations. Here, robotic stackers use vacuum grippers or clamp heads to build pallets layer by layer, rotating and interlocking packs to maintain balance and optimize density. Slip sheets or corner boards may be inserted for additional stability. Once complete, each pallet enters a rotary stretch wrapper, where clear plastic film is wrapped under tension around the stack, binding it tightly to protect against vibration or shifting during transport. A thermal label is printed and applied to the outer film, displaying destination, pallet ID, and manufacturing metadata. Every part of the line, from syrup mixing to final wrapping, is connected to a centralized control system, often SCADA-based, which aggregates data from thousands of sensors across the production floor. It tracks real-time flow rates, fill volumes, pressure changes, CO2 consumption, label placement accuracy, packaging efficiency, and quality checkpoints. Alerts are triggered the moment a parameter deviates from its programmed limits, prompting either automatic correction by servo-driven actuators or shutdown protocols to isolate the issue for inspection. Quality assurance is deeply embedded into the process. Sample bottles and cans are pulled at regular intervals by robotic pickers and sent to adjacent quality labs, where automated instruments test for Brix levels, carbonation volume, pH, color density, and turbidity. Gas chromatographs may analyze flavor profile consistency, and oxygen analyzers confirm shelf life integrity. Retention samples are archived from each production batch in cold storage, enabling full traceability in case of future inquiry. Cleaning in place systems activate between flavor runs or at set intervals, flushing pipes, tanks, and filling valves with heated caustic solutions, followed by acid rinses, and finally with purified water. All internal product contact surfaces are sanitized, and the data logs are updated with each wash cycle. This ensures the system is sterile before the next production batch begins, whether it's more Coca-Cola or a different product line altogether. All along the line, mechanical timing is critical. Bottles that arrive milliseconds too soon or too late can cause backup or collision, so every machine is programmed to respond to product flow, spacing, and acceleration. Timing screws, sensors, and motorized star wheels maintain precise positioning, and buffer conveyors absorb temporary surges without stopping the line. Overhead, cameras and inline vision systems inspect every package for branding alignment, color accuracy, seal integrity, and tamper evidence, discarding any product that fails visual QA. From a distance, the system appears to operate like a single, unified machine: syrup, water, gas, packaging, and automation all working as one organism, never pausing, never deviating. Every bottle and every can moves through this stream of equipment with exacting control, shaped not by hand, but by air pressure, centrifugal force, liquid dynamics, and heat energy, and by the software that orchestrates it all behind the scenes. The production of cherry Coca-Cola begins with the coordinated movement of ingredients through a tightly integrated system of tanks, pipes, mixers, fillers, and control panels, where every second of the process is timed, and every variation in flow, pressure, or temperature is monitored and corrected in real time. The defining element of this beverage, the distinct cherry-flavored profile, requires its own set of ingredients to be introduced at specific intervals within a continuous fluid stream, and the entire operation is driven by automation that ensures each bottle or can delivers the same flavor, carbonation, and experience without deviation. At the heart of the operation lies the mixing zone, a sealed chambered area of the factory where the formulation begins, not with bottles or packaging, but with the controlled blending of ultra-purified water and concentrated syrup. The water itself is subjected to a multi-stage filtration process that removes every mineral and contaminant through reverse osmosis membranes, UV sterilization lights, activated carbon beds, and deionization columns. The final water output is chemically neutral, consistent in temperature, and free of flavor interference, ensuring it will not alter or dull the delicate cherry infusion that characterizes the product. Simultaneously, the cherry Coca-Cola-based syrup is prepared in mixing tanks where measured amounts of sweeteners, flavor agents, acidity regulators, and natural cherry extracts are combined into a thick, dark syrup with precise viscosity. Each batch is homogenized with high-speed impellers, continuously monitored for density using inline refractometers, and sampled through sterile taps for real-time verification of its sugar content, aroma, and visual clarity. Once verified, the syrup is stored in insulated holding tanks fitted with agitators to prevent settling and ensure uniformity prior to dosing. When the purified water and cherry-infused syrup are combined, they are fed into high shear blending, chambers where specially engineered turbines swirl the mixture at controlled speeds to ensure total integration. These blending units include flow regulators that adjust the syrup to water ratio down to 0.1% so that every liter leaving the chamber maintains exact sweetness and acidity levels. This blending is continuous and uninterrupted, forming a central stream of cherry Coca-Cola base that is directed toward the chilling loop. Before carbonation, the mixture is rapidly cooled using a set of plate heat exchangers where cold glycol fluid moves through alternating stainless steel plates, drawing heat from the beverage as it flows in an adjacent channel. The cooling process is essential, dropping the beverage temperature to near freezing, around 0 to 2 degrees Celsius, which allows the carbon dioxide to be absorbed efficiently and held within the liquid under pressure. Once chilled, the drink enters a sealed carbonation unit. Inside this pressurized chamber, carbon dioxide gas, stored in liquid form at cryogenic temperatures, is vaporized, filtered, and then injected into the cold cherry Coca-Cola base through a sparging system that disperses the gas evenly throughout the liquid. The CO2 dissolves into the beverage instantly due to the low temperature and high pressure, and the resulting carbonated drink flows forward to the buffer tanks, where it is gently mixed and held under pressure to prevent gas release or foaming. These buffer tanks act as holding silos between mixing and filling, maintaining consistent temperature and carbonation levels while regulating the supply to each individual filling line. The tanks are fitted with pressure sensors, degassing valves, and agitation paddles that rotate at slow speeds to preserve homogeneity without disturbing the carbonation level. From here, the carbonated cherry Coca-Cola is ready to be dispensed into containers at high speed. If bottles are the intended format, production begins with PET preforms, small test tube-shaped plastics that are loaded into feed trays and passed through a rotating oven chamber fitted with infrared heaters. The preforms are warmed to a pliable temperature before being inserted into steel molds, where compressed air blows each preform into the shape of a bottle within milliseconds. The molds are cooled, and the newly formed bottles are ejected onto conveyor lanes, where they begin their journey to the filling line. Each bottle passes through an inversion unit, where they are turned upside down and rinsed with filtered air or ionized water to eliminate static charge and remove any residual particles. Once cleaned, they are flipped back upright and enter the filling carousel, a large rotating ring with multiple filling heads. As each bottle passes underneath a head, it is sealed airtight and filled using counter-pressure filling. CO2 is first used to purge oxygen from the bottle. Then the beverage is dispensed, equalizing pressure to avoid foaming or gas loss. As the bottle fills, a level sensor determines the precise volume, and flow is shut off with a clean break once the target fill is reached. The next stage is capping. Cap hoppers sort and orient the plastic caps, feeding them down a chute where robotic arms place each cap onto the filled bottle. A torque-controlled spindle tightens every cap to an exact specification, and a vacuum sensor checks that each seal is secure. Each bottle then passes through a high-speed date printer that applies production information, including line number, time code, and expiration date. Can filling follows a similar track, but on a separate line with specialized machinery. Empty aluminum cans arrive pre-formed, palletized, and stacked in tall columns. These stacks are depalletized and fed into the can rinsing tunnel, where they are cleaned with a high-pressure deionized water spray, then dried using high-speed air knives. Cleaned cans are conveyed directly into the filling system, where they pass beneath a gas flush station that replaces internal air with carbon dioxide to maintain freshness. As the cherry Coca-Cola is dispensed into each can, the filling head retracts, and a lid is placed onto the top of the filled can by a precision seamer. This machine uses a dual-action compression and curl technique to lock the lid onto the can body, creating a hermetic seal. Immediately afterward, the can is cleaned again externally, printed with production codes, and passed to the packaging lanes. At this point, both bottles and cans converge into the secondary packaging area, where products are grouped, aligned, and prepared for shipment. Bottles are collected into multi-packs using servo-controlled arms that lift and guide them into shrink film, which is wrapped and sealed around the group before passing through a heat tunnel that shrinks the film tight. Cans are guided into multi-lane collators that align sets of 6, 12, or 24, depending on the package, and apply either shrink wrap or cardboard wraps printed with branding and barcodes. Cameras verify each pack's alignment, color fidelity, and integrity before they are cleared for stacking. Packaged units move toward robotic palletizing systems, where vacuum lifters and grip arms organize them into stable layers, rotating the orientation of each pack to create interlocking rows. Slip sheets are inserted between layers, and once the pallet reaches full height, it is transferred into an automatic stretch wrapper, which encases the pallet with tensioned film from top to bottom. A printed label with barcodes, destination data, and production batch is applied to the outside, and the pallet is transferred to the loading dock for transport. Meanwhile, every single movement on the production floor is tracked by an integrated control system, a network of programmable logic controllers and interface stations that monitor temperature, pressure, syrup ratios, carbonation levels, fill rates, and flow speed. The system adjusts each parameter in real time. If syrup density increases due to ambient temperature, pumps slow fractionally. If bottle alignment drifts off center, the guide rails shift laterally. If carbonation drops even slightly, the gas injector valve pulses at higher frequency until the correct level is restored. Throughout the process, Quality assurance teams collect real-time data from sensors and pull physical samples at intervals. These samples are sent to inline labs, where technicians run automated tests using densitometers, CO2 analyzers, pH probes, and colorimeters to ensure each bottle or can meets flavor, appearance, and stability specifications. A taste panel may confirm final flavor consistency before the batch is cleared for release, and a retention sample is archived for traceability. Between batches, the entire system undergoes a clean-in-place (CIP) procedure. Pipes, valves, tanks, and filling heads are flushed with heated alkaline solutions, followed by acidic rinses and sterilization stages. Sensors monitor residue levels in rinse water, and the system will not allow a new batch to begin until cleanliness thresholds are met across the entire line. Inside the production facility dedicated to Coca-Cola Zero, the operation begins with a steady rhythm of systems calibrated to blend, chill, carbonate, and package a product that relies on absolute precision. Because unlike its sugar-sweetened counterparts, Coca-Cola Zero is formulated with no sugar at all, relying instead on an exact balance of non-nutritive sweeteners that must be handled with extraordinary control to maintain both flavor integrity and regulatory compliance. The process begins, not with packaging, not even with carbonation, but with water. Water that has been stripped of every mineral, ion, and microbe through a comprehensive purification chain that includes activated carbon filtration, multi-stage reverse osmosis membranes, ultraviolet sterilization, and final stage polishing filters to ensure that every molecule entering the blend tanks is completely neutral. This water, once purified, is cooled immediately and transferred into a network of stainless steel supply tanks, each one connected to high-flow dosing manifolds, where the Coca-Cola Zero concentrate is introduced. Unlike other formulas, the Coca-Cola Zero syrup contains highly sensitive ingredients that must be mixed with close control over both flow rate and agitation speed. A series of variable speed turbines inside a baffled blending chamber begins to stir, drawing in sweetener concentrates from microdosing pumps which meter out fractions of grams per second, ensuring that every liter of finished product will contain only the approved quantity of aspartame, acesulfame potassium, and other formulation components. The syrup is mixed with chilled, purified water in a continuous loop, constantly circulating through inline density sensors and refractometers that verify every measurable characteristic of the mixture: its Brix equivalent, its acidity level, its color profile, and its consistency, all monitored by SCADA systems that relay performance data to centralized control stations positioned throughout the factory floor. If the syrup becomes too concentrated, water flow is increased fractionally. If any temperature drift is detected in the mixing tank, the coolant jacket is adjusted to compensate instantly. The goal is absolute uniformity. Every second, every drop must match the one before it. As the base liquid moves into the carbonation stage, it passes through a final chilling module where its temperature is brought down to a near freezing range. At this point, the beverage is ready for carbonation. The carbon dioxide gas, stored in its own cryogenically cooled system, is injected into the mixture using a high-efficiency carbonator, a pressurized steel chamber, where the CO2 enters under regulated pressure through micro-diffusers, creating billions of microscopic bubbles that dissolve immediately into the cold liquid. The flow of CO2 is continuously calibrated according to beverage temperature, system pressure, and product viscosity, with flow sensors and back pressure valves maintaining stability as thousands of liters pass through each hour. Once fully carbonated, the beverage is routed into pressurized holding tanks, buffer vessels that serve as the final point of quality assurance before the product reaches the filler. These tanks are lined with level indicators, gas traps, and temperature probes, all synchronized to maintain the carbonation level while gently agitating the liquid to prevent stratification or foaming. Here, any final testing is performed in line. Carbonation volume, turbidity, residual sweetness, and pH are verified one last time. A sampling valve allows automated collection of product every few minutes, and that sample is passed directly into a micro lab for flavor standardization analysis using spectrophotometry and gas chromatography. Meanwhile, the packaging line is already in motion. For plastic bottles, the process starts with injection molded preforms, small and thick-walled, which are delivered in bulk and stored in hoppers above the blow molding machines. These preforms descend through a heater array where infrared panels warm them to a precise forming temperature before they are dropped into two-part molds. Compressed air is blasted inside, expanding the plastic against the inner mold walls to create full-size bottles instantly. As the mold opens, cooled air is used to solidify the bottle's shape, and a robotic gripper places each new bottle upright onto a moving conveyor that feeds directly toward the filling station. Before any liquid enters the bottles, they are passed through an inverted rinsing tunnel where ionized air is sprayed inside each one to remove microscopic particles. They continue along the line toward the filler, where a rotary system spins each bottle into place beneath a filling valve. This valve descends into the mouth of the bottle, creates a pressurized seal, and initiates a filling sequence that begins with a brief CO2 purge to eliminate oxygen and preserve shelf stability. The pressurized beverage flows into each bottle in just under 2 seconds, with real-time fill level sensors using laser measurement to verify that each container is consistent to the milliliter. There is no overflow, no foam rise, no turbulence. The pressure balancers are engineered to make the fill seamless and silent. Once filled, the bottles pass immediately to the capping turret. High-speed feeders deliver bottle caps from a bowl sorter into the capping head, which presses each cap onto the threads and twists them into place using torque-monitored spindles. Each cap is verified for application tightness and angle, and a vacuum test is performed at random intervals by an inline tester that verifies the seal by measuring pressure drop inside a chamber. If a cap is misapplied, the bottle is instantly diverted from the line. After capping, the bottles pass through a date and batch printer, which uses thermal inkjet or laser etching to apply identification directly to the neck or shoulder of the bottle, depending on line configuration. In parallel, aluminum cans are prepared on their own dedicated track. Delivered by the pallet, preformed cans are depalletized and sent through a high-speed depuck system that guides them into the line one at a time. Each can passes under a rinse sprayer and then through a drying tunnel before entering the can filler. This equipment is built for volume. Multiple nozzles dispense product simultaneously, filling dozens of cans per second, each one pressurized beforehand to prevent foaming during the rapid fill. A lid is placed on each can immediately after filling, and a seam roller presses the lid onto the body, creating a hermetic seal that is pressure tested, scanned by vision systems, and validated against a standard profile. Cans are printed with batch codes and transferred to the packaging section. Now, both bottles and cans proceed to the secondary packaging area, where multi-packs are created using automated grouping systems. Bottles are collated into clusters of 6, 12, or 24, wrapped tightly in shrink film, and sent through a steam tunnel that shrinks the plastic smoothly around the group without obscuring the labels. Cans are similarly grouped and placed into printed cardboard sleeves or plastic rings, depending on the destination. Each group is weighed, scanned, and inspected for alignment before being transferred into cartons. Carton erectors form boxes from flat stock, fold them automatically, and glue them using hot melt adhesives before they are filled with packs by robotic arms that stack them precisely inside. Once loaded, the cartons are sealed, labeled, and conveyed to a palletizing system where mechanical arms stack them onto pallets in programmed patterns to maximize space and stability. A slip sheet may be inserted between layers, and once the stack is complete, it moves into a stretch wrapper that encases the pallet with plastic film to lock it tight for shipping. The entire pallet is weighed, labeled, and scanned before being queued for loading. Red Bull starts with its formula, a carefully guarded blend of ingredients that deliver its characteristic taste, texture, and functional effects. At the heart of the recipe is water, which serves as the main ingredient by volume. This water is not simply pumped from a municipal source and used directly. It undergoes multiple purification stages to ensure it is free of any dissolved solids, minerals, or microorganisms that might alter the taste or stability of the drink. The purification typically begins with coarse filtration to remove particulate matter, followed by activated carbon filtration to strip out organic compounds and chlorine, then reverse osmosis to achieve a very low mineral content. The final step often involves ultraviolet light treatment or ozonation to sterilize the water before it enters the production tanks. Once the water is ready, the remaining ingredients are prepared. These include sucrose and glucose for sweetness and energy, citric acid for acidity and flavor balance, taurine as a functional amino acid, caffeine as the stimulant, and B group vitamins like niacinamide pantothenic acid, vitamin B6, and vitamin B12. Each of these arrives at the factory in bulk form. Sugars as fine crystals, taurine and caffeine as purified powders, vitamins as either powders or highly concentrated solutions. All are stored under controlled conditions and tested in an in-house quality lab for purity and potency. The creation of the beverage begins with the preparation of a concentrated syrup. In large stainless steel blending vessels, precise amounts of sugar are dissolved in purified water under gentle heat, usually between 50 and 60 degrees Celsius, to speed dissolution without caramelizing the sugar. The glucose syrup, if used in liquid form, is pumped directly into the blending vessel through sanitary pipelines. Once the sugars are fully dissolved, the other functional ingredients, taurine, caffeine, and vitamins, are added in carefully measured doses. This mixing process is critical. Operators rely on automated ingredient dosing systems connected to load cells and flow meters to ensure exact quantities, as even a small deviation could alter flavor or regulatory compliance. Citric acid is then introduced to adjust the pH, giving Red Bull its slightly tart backbone and enhancing stability. Flavors, which are part of a proprietary blend, are also incorporated at this stage. These may include natural and artificial components that together create the drink's distinctive aroma and taste. The mixing tanks are fitted with high-speed agitators to ensure uniform distribution of all ingredients, and the resulting syrup is tested in the lab for Brix, acidity, and flavor profile before moving forward. Once the base syrup is complete, it is diluted with more purified water to bring it to the target concentration for the finished beverage. This final liquid mixture, now containing all flavor and functional components, is chilled to prepare it for carbonation. Carbonation is one of the defining aspects of Red Bull's sensory experience, and it is performed with great precision. The chilled beverage passes through a carbonator where it is brought into contact with carbon dioxide under high pressure. The CO2 dissolves into the liquid with the level carefully controlled. Too little carbonation would make the drink taste flat, while too much could affect mouthfeel or cause excessive foaming during filling. The carbonated beverage is then immediately directed to the filling lines. Red Bull is packaged almost exclusively in aluminum cans, chosen for their lightweight nature, excellent barrier properties against light and oxygen, and recyclability. These cans arrive at the factory in massive stacks of unprinted or pre-printed containers, each one spotless and free from dents or imperfections. Before filling, they undergo a thorough rinse with deionized water or ionized air to remove any dust or debris. The rinsed cans move down the line on high-speed conveyors into the filling carousels. The filling process operates at incredible speed. often hundreds of cans per minute, and is performed in a pressurized environment to maintain carbonation. Each can is filled from the bottom up to minimize turbulence and foaming, then immediately sealed with an aluminum end by a seaming machine. This seam is a precision crimping of the lid to the can body, creating an airtight and watertight seal. Once sealed, each can is inverted briefly to ensure the lid is fully sanitized by contact with the beverage inside, then returned upright. Immediately after sealing, cans pass through automated inspection systems. These use a combination of cameras, sensors, and weight checks to identify any underfilled, overfilled, or defective cans. Any can that fails inspection is automatically rejected and diverted from the main conveyor. Approved cans move on to pasteurization or cold sterilization, depending on the plant's process design. Pasteurization involves heating the cans to a specific temperature for a set time to ensure microbial stability, while cold sterilization uses aseptic filling combined with sterilized containers to achieve the same result without heat. Once the cans are confirmed safe and stable, they head to the secondary packaging area. Here, they are grouped into the familiar 4-packs, 6-packs, or larger cases using cardboard wrap or shrink film. Automated cartoners or shrink wrappers handle this at high speed, often in combination with robotic case packers that load the multi-packs into corrugated shipping cases. The shipping cases are sealed with tape or hot melt glue, coated with batch information for traceability, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability and transported to a climate-controlled warehouse. Although Red Bull is shelf-stable at room temperature, storage away from excessive heat or direct sunlight helps maintain carbonation and flavor over time. From the warehouse, pallets are loaded onto trucks bound for distribution centers and retailers. Given Red Bull's global reach, many of these pallets also enter intermodal shipping containers for transport by rail or sea to other countries. Throughout production, the emphasis on quality and consistency is relentless. Every batch of syrup and finished beverage undergoes analytical testing to confirm caffeine content, vitamin levels, acidity, and carbonation. Sensory panels taste samples to ensure the flavor matches the established profile. On top of that, microbiological testing verifies that no harmful organisms are present, and shelf life trials confirm that the product will remain stable through its intended storage period. The machinery in a Red Bull plant is highly automated, reducing human contact with the product to a minimum. Operators oversee systems via control rooms equipped with touchscreens that display real-time data on mixing temperatures, carbonation levels, filler speeds, and line efficiency. Maintenance crews work behind the scenes to keep pumps, compressors, and conveyors in top condition, as any downtime on a high-speed beverage line can be costly. Sustainability is also a growing focus in Red Bull production. Aluminum cans are already among the most recyclable packaging formats, and many plants source cans with a high percentage of recycled content. Water purification systems are designed to minimize waste, and heat recovery from pasteurization can be used to preheat water for syrup preparation. Efficient compressors and motors reduce energy consumption, and many facilities work to optimize transport logistics to cut fuel use in distribution. What makes the Red Bull process particularly interesting is how tightly controlled and repeatable it must be. The drink's formula is identical worldwide, which means a can produced in Austria should taste exactly the same as one produced in the United States or Asia. Achieving this level of uniformity across multiple plants requires not only identical recipes and ingredients, but also standardized equipment, operating procedures, and quality control protocols. Every plant is essentially a mirror of the others, ensuring that no matter where it's made, Red Bull delivers the same signature flavor, carbonation, and energizing effect. Every can of Monster begins with its ingredients, and the largest component is water. The water used in Monster Energy production is not simply drawn from a tap, it is subjected to a thorough purification process to remove any dissolved solids, organic compounds, or microorganisms that could affect taste, appearance, or stability. The typical sequence starts with coarse filtration to catch sediment, followed by activated carbon filters to strip out chlorine and odors. Reverse osmosis membranes then reduce mineral content to near zero, creating a blank canvas for the flavor formulation. As a final step, ultraviolet light or ozone is used to sterilize the water before it enters the mixing tanks. Next come the sweeteners, functional additives, acids, and flavors that give Monster its distinctive taste and energy-boosting profile. Cane sugar or beet sugar may be used along with glucose or high fructose corn syrup, depending on the variant and market. These sugars arrive in bulk either as crystalline solids or liquid syrup in tanker trucks. Functional ingredients include caffeine for stimulation, taurine as an amino acid additive, and B vitamins like niacin, riboflavin, vitamin B6, and vitamin B12 to support energy metabolism. Some varieties incorporate plant extracts such as ginseng or guarana, which add both flavor and functional appeal. Acids like citric and sometimes malic acid adjust the pH for tanginess and preservation, while natural and artificial flavors create the unique profile for each Monster variety, from the classic green logo flavor to tropical, coffee-based, and sugar-free blends. The first main step in production is the preparation of the concentrate or syrup. In large stainless steel mixing vessels, sugar is dissolved into heated purified water under gentle agitation. If liquid sweeteners are used, they are pumped directly in and blended. Functional powders like caffeine and taurine are carefully weighed and added in controlled sequences to ensure complete dissolution without clumping. B vitamins, which are sensitive to heat, are typically added later in the process to preserve potency. The plant extracts, if used, are measured and incorporated at specific points, often emulsified, to ensure they disperse evenly throughout the drink. Flavor concentrates, which can be highly potent, are metered into the mix using precision dosing pumps. These concentrates often contain a mixture of flavor oils, sweeteners, and acids in a stable base that integrates easily into the water-sugar matrix. Because Monster produces a wide variety of flavors, the plant must be capable of switching from one concentrate to another with minimal downtime. A challenge that requires clean-in-place systems to flush and sanitize mixing tanks and pipelines between batches. Once the syrup is fully blended, it is tested in the quality control lab for sweetness, acidity, caffeine content, and flavor profile. The lab team uses sensory analysis alongside instrumental testing to ensure the mixture matches the established standard. Only when it passes these checks is it moved forward. The next stage is dilution and carbonation. The concentrated syrup is blended with additional purified water in large batch tanks to reach the target formulation for the finished drink. This diluted beverage is chilled to near freezing temperatures to maximize the solubility of carbon dioxide during carbonation. The chilled liquid enters a carbonator, where CO2 is injected under high pressure and mixed through fine diffusers or inline mixers. The carbonation level is closely controlled. Too little, and the drink will taste flat. Too much, and it will foam excessively during filling. Once carbonated, the beverage moves immediately to the filling lines. Monster Energy is almost always packaged in aluminum cans, chosen for their lightweight, barrier properties, and recyclability. These cans arrive at the plant in massive pallets of unfilled containers, often printed with Monster's signature claw mark logo and variant-specific graphics. Before filling, each can is inverted and passed through a rinser, which uses either deionized water or ionized air to remove any dust or particles. The cans travel into high-speed rotary filling machines where they are filled from the bottom up to reduce foaming and preserve carbonation. Each filler head dispenses an exact volume, ensuring every can meets legal net content OMA requirements. Immediately after filling, the cans pass into a seaming machine, where an aluminum lid is placed on top and mechanically rolled into place to form a double seam that locks the contents in airtight. This seaming process is a critical control point. Improperly sealed cans can lose carbonation or leak, so seamer performance is constantly monitored. Sealed cans are inverted briefly so that the liquid inside can contact the underside of the lid, which acts as a quick sterilization step. Depending on the plant's process, the cans may then undergo tunnel pasteurization. Moving through a heated water spray tunnel that raises the beverage temperature for a specific time to kill any microorganisms. Or may rely on aseptic filling techniques that eliminate the need for heat treatment. Once pasteurized or otherwise stabilized, the cans are cooled rapidly to prevent heat damage to vitamins and flavors. They then pass through a series of inspection systems. Automated vision cameras check for dents, damaged seams, or incorrect graphics. Check weighers ensure that each can contains the correct amount of product, and any deviation triggers an automatic rejection. Many lines also incorporate inline gas analysis to confirm carbonation levels in the finished product. The approved cans move into the secondary packaging area, where they are grouped into multi-packs. This may involve cardboard carriers, shrink-wrapped bundles, or trays depending on the market. Automated packers arrange the cans in the correct pattern, wrap or enclose them, and send them toward the case packing stage. Here, multi-packs are loaded into corrugated shipping cartons, which are sealed, coated with batch and date information, and stacked by robotic palletizers. Pallets are wrapped in stretch film to secure the load and sent to the warehouse for storage. Even though Monster Energy is shelf-stable at room temperature, it is generally stored in cool, dry conditions to maintain flavor and carbonation quality. From the warehouse, products move through distribution networks to retail shelves worldwide. Behind all of these steps is a rigorous quality control program. The production team pulls samples at every stage: syrup preparation, dilution, carbonation, filling, and post-packaging to confirm compliance with product specifications. Analytical labs test for caffeine content, sugar level, vitamin potency, pH, and carbonation. Microbiological testing ensures that no spoilage organisms are present. Sensory panels evaluate taste, aroma, and mouthfeel to maintain brand consistency. The machinery that makes this possible is heavily automated. Operators work from control panels in climate-controlled rooms, monitoring temperatures, pressures, flow rates, and carbonation levels via touchscreen interfaces. Programmable logic controllers coordinate the entire process, from mixing through palletizing, and sensors throughout the plant send real-time feedback. This automation allows Monster to produce enormous volumes with minimal downtime, while meeting strict safety and quality standards. Sustainability considerations are increasingly built into Monster's operations. Aluminum cans are highly recyclable, and many suppliers provide them with a significant proportion of recycled content. Water purification systems are designed to recover and reuse as much water as possible in non-product applications like cooling or cleaning. Heat from pasteurization is often recovered and used to preheat water for syrup preparation, reducing energy demands. Transportation logistics are optimized to reduce emissions, and some plants have moved towards renewable energy sources for part of their power. What is most striking about Monster Energy production is its consistency. The brand's image may be chaotic and wild, but the drink inside is the product of careful, repeatable processes that leave nothing to chance. Every step is measured, every variable tracked, every can inspected, ensuring that when a consumer pops the tab, and hears that sharp hiss of carbonation, they get exactly the flavor, mouthfeel, and energy hit they expect, whether they bought it in a gas station in California or a convenience store in Seoul. The making of a can of Celsius Energy is a study in a modern beverage manufacturing where health-focused marketing meets industrial-scale precision. Although the drink is promoted as a fitness or metabolism-boosting energy beverage, the underlying production process is much like that of other carbonated functional drinks. A carefully balanced formula of water, sweeteners, active ingredients, and flavors blended, carbonated, and packaged under conditions designed to maintain purity, consistency, and shelf stability across millions of units. It begins with the most abundant ingredient, water. Water quality is paramount in Celsius production because any dissolved minerals, organic matter, or off flavors could interfere with the delicate flavor balance and the stability of the added functional ingredients. Purification is achieved through a series of treatments. First, the incoming water is screened through coarse filters to remove particles. Activated carbon filters then strip out chlorine, residual odors, and organic compounds. Reverse osmosis membranes reduce dissolved solids to extremely low levels, creating a neutral base. Finally, ultraviolet light or ozonation is applied to sterilize the water before it enters the formulation tanks. Once the water supply is ready, the functional and flavor ingredients that distinguish Celsius are prepared. Unlike traditional energy drinks that lean heavily on sugar and caffeine alone, Celsius incorporates a blend of caffeine from both synthetic and natural sources, such as green tea extract and guarana seed extract. It also features taurine, B vitamins, vitamin C, and in many varieties, additional plant extracts such as ginger root extract for a warming, metabolism-supporting effect. Some variants are sweetened with cane sugar, while many zero sugar options use non-nutritive sweeteners like sucralose or stevia extract. Acids like citric acid and malic acid are used to balance the flavor profile and help preserve freshness, while natural flavors, often fruit-based, create the distinct taste of each variety, from sparkling orange to peach vibe. The first major step in production is creating the base concentrate or syrup. This happens in large stainless steel mixing vessels equipped with high shear agitators or propeller mixers to ensure complete dispersion of both solids and liquids. For sugar-containing variants, crystalline sugar is metered into the purified water and dissolved at a controlled temperature to speed up the process without causing caramelization. If the formula calls for 0-calorie sweeteners, these are introduced in microgram precise quantities via automated dosing systems, as their sweetness intensity is many times greater than that of sugar. Functional powders, such as caffeine, taurine, and vitamin C, are weighed with laboratory-grade scales before being added. Plant extracts often arrive as liquid concentrates or fine powders and may require pre-dissolution in a small amount of water or glycerin to ensure they blend smoothly without clumping. For heat-sensitive ingredients like vitamin C, addition occurs towards the end of mixing to minimize degradation. Throughout this stage, the pH is monitored and adjusted as needed, since certain active compounds are more stable within specific acidity ranges. Once all solids are dissolved and liquids are homogenized, flavoring compounds are introduced. These may be natural fruit essences, essential oils, or compounded flavors from specialist suppliers. The flavoring process is highly sensitive. Even slight, over, or underdosing can shift the sensory profile away from the established standard. The completed syrup is sampled and sent to the in-house quality control laboratory for analysis. There, technicians measure sugar concentration, acidity, caffeine content, and other activities, and conduct sensory evaluations to confirm taste matches the reference profile. After passing these checks, the syrup is diluted with more purified water to the final formulation strength in large batch tanks. At this stage, the beverage is chilled to near freezing temperatures in preparation for carbonation. Carbonation is one of the signature sensory features of Celsius's sparkling varieties, and it is carried out with precise control over dissolved CO2 content. The chilled liquid flows into a carbonation unit where carbon dioxide gas is injected under pressure, dissolving evenly into the liquid. The goal is to achieve a crisp, sparkling mouthfeel without excessive foam that could cause filling issues. From the carbonator, the beverage is pumped directly to the filling lines. Celsius is typically packaged in slim aluminum cans, often the 12-ounce or 355 milliliter size, chosen for their portability, shelf life stability, and recyclability. The empty cans arrive at the plant in palletized stacks and are fed onto conveyors. Before filling, they undergo a rinse using ionized air or deionized water to remove any dust or particles. The cleaned cans are inverted, then righted, and sent into the filling carousel. The filling process operates at high speed, often hundreds of cans per minute, and is done under conditions that protect carbonation. Each filler head dispenses an exact volume from the bottom up to reduce turbulence. Immediately after filling, the cans move into a seaming machine, where an aluminum lid is placed on each and mechanically crimped to form an airtight seal. This seam is a critical element of the can's integrity, and seaming stations are regularly checked with seam micrometers to verify proper formation. Sealed cans may pass through a pasteurization tunnel, depending on the plant's preferred stability method. In pasteurization, the cans travel along a conveyor under sprays of hot water that raise the internal beverage temperature to a specific target for a defined time, killing any potential microorganisms. Afterward, the cans are cooled quickly to protect heat-sensitive nutrients. In some plants, aseptic filling technology is used instead, allowing the drink to be filled into sterilized cans without the need for post-fill heat treatment, which can better preserve delicate flavors and vitamins. Once cooled, the cans pass through a series of inspection systems. Vision systems scan for dents, label defects, or improper graphics. Checkweighers ensure the net content is correct, and any can outside the tolerance is automatically rejected. Inline gas analyzers may measure CO2 content to confirm carbonation consistency. Approved cans enter the secondary packaging stage, where they are grouped into multi-can packs. Cardboard sleeves, shrink film, or tray packs are applied depending on the distribution plan. Multi-packs are collated into corrugated shipping cases, which are sealed with glue or tape and printed with batch codes for traceability. Robotic palletizers stack these cases onto pallets in stable patterns, after which the pallets are wrapped in stretch film to secure them for transport. The finished pallets move into climate-controlled warehouse storage. Celsius products are shelf-stable, but temperature control helps maintain flavor, carbonation, and nutrient stability over the shelf life. From here, pallets are shipped to distributors, retailers, and online fulfillment centers worldwide. Throughout this process, quality control is constant. Samples from each batch are tested for caffeine level, vitamin potency, flavor accuracy, pH, and carbonation before release. Microbiological tests ensure no spoilage organisms are present. Sensory panels evaluate the finished drink for mouthfeel, aftertaste, and aroma, comparing it to the brand standard. Because Celsius positions itself in the better-for-you beverage category, consistency in active ingredient content is especially critical, and certificates of analysis often accompany each production run. Behind the scenes, this is all enabled by a network of highly automated equipment controlled by programmable logic controllers. Operators monitor the process from control stations, adjusting parameters like mixing speed, carbonation pressure, or filler settings as needed. The plant's clean-in-place systems allow tanks, pipelines, and fillers to be washed and sanitized automatically between batches, ensuring hygiene without extended downtime. Sustainability is an increasing focus in Celsius production. Aluminum cans are infinitely recyclable, and many suppliers now provide cans with a high percentage of recycled content. Plants work to reduce water use in cleaning and cooling, recover heat from pasteurization to preheat processed water, and optimize transport routes to cut emissions. Some facilities integrate renewable energy into their operations, such as solar panels or purchase agreements for green electricity. What makes the Celsius production process interesting is the careful balance between functional beverage science and mass-market beverage engineering. While the plant extracts and nutrient additions require precise handling to maintain potency and stability, the large-scale manufacturing environment demands speed and efficiency. The result is a beverage that can deliver consistent taste, carbonation, and nutritional content across millions of cans, while supporting the brand's positioning as a lifestyle-oriented, health-conscious energy drink. Beer begins with bubbling vats of barley and hops transforming into golden liquid under precise control. Bicardi's rum flows from towering columns of molasses and copper stills, while Jack Daniel's whiskey ages in charred oak barrels deep in Tennessee warehouses. Today, we go inside the world's most famous drink factories to see how centuries of craft, chemistry, and fire combine to create the spirits that fuel celebration across the globe. It all starts with malted barley, the soul of the beer. In a factory setting, the malt arrives by truckloads or freight trains already malted at a dedicated malting facility. Malting is a process in itself. Barley is soaked, allowed to germinate just enough to activate enzymes, and then dried and kilned to stop the growth. This controlled germination unlocks starches and enzymes that will later convert to fermentable sugars. The exact roast of the malt, pale, caramel, a chocolate, black, determines much of the final beer's color and flavor. For large-scale beers, base malts are used, usually lightly kilned, with small amounts of specialty malts blended in. The malt is piped into massive silos at the brewery, where it's stored dry and clean. When brewing begins, the malt is sent through a series of conveyors or airlifts to the mill. Here, roller mills crush the grain, not into flour, but into coarse grist. The idea is to crack the husk while leaving the interior accessible. Too fine, and the mash will become sticky and hard to filter. Too coarse, and sugar extraction drops. The grist is collected and weighed, then transported directly to the mash tun where the real transformation begins. In the mash tun, often a stainless steel vat the size of a swimming pool, the grist is mixed with hot water to form a thick porridge-like slurry. This step, called mashing, activates enzymes like amylase, which convert starches into simple sugars. The temperature is held precisely, usually around 65 and 68 degrees Celsius, depending on the style of beer. Too hot and the enzymes are denatured. Too cold and the starches won't fully convert. The mash is gently stirred using mechanical arms to ensure uniformity. For the next hour or so, the grain slowly transforms into a sweet liquid known as wort. When conversion is complete, the mash is transferred to the lautering vessel, sometimes built into the same tank. Lautering is the process of separating the liquid wort from the spent grain. A false bottom or fine slotted plates allow the liquid to drain through, while the grain bed itself acts as a natural filter. More hot water, known as sparge water, is sprayed over the top to rinse out every last bit of sugar. The collected wort flows to the brew kettle, while the spent grain, now protein-rich but sugar-poor, is conveyed out of the system. Many large breweries donate or sell this grain to farms as cattle feed. Next is the boil. In towering stainless steel kettles, the wort is brought to a rolling boil and held there for 60 to 90 minutes. This step sterilizes the liquid, halts enzymatic activity, and causes unwanted proteins to coagulate and fall out of suspension. It's also when hops are added. Hops are the cone-shaped flowers of the Humulus lupulus plant, prized for their bitterness, flavor, and aromatic oils. In a factory setting, Hops usually arrive as compressed pellets for consistency. Early additions bring bitterness. Late additions and whirlpool hops contribute aroma and flavor. Boiling is carefully managed. A powerful steam jacket heats the vessel, while a system of condensers captures volatile compounds and steam vapor to reduce environmental impact. The smell during this stage is unmistakable. Sharp, herbal, sweet, and slightly pungent. It's the moment beer begins to take on its final character. After the boil, the wort must be rapidly cooled. This happens in a plate heat exchanger, where hot wort flows past cold water or glycol in alternating metal plates. Temperatures drop from near boiling to fermentation ready, usually between 10 degrees Celsius and 20 degrees Celsius, in just seconds. In most large breweries, the water used to cool the wort is captured and reused to preheat the next batch, conserving energy. From there, the chilled wort is transferred to fermentation tanks, colossal, conical bottom vessels made of polished stainless steel. Some are the size of small buildings. This is where the magic really happens. Yeast is introduced, either ale yeast or lager yeast. Yeast begins feeding on the sugars in the wort, producing alcohol and CO2 as byproducts. The tanks are fitted with sensors that monitor temperature, pressure, and gravity in real time. If fermentation is too vigorous, pressure is vented. If it's too slow, temperature can be nudged to wake up the yeast. Fermentation can last from a few days for ales to several weeks for lagers. During this time, brewers pull samples to test for alcohol levels, residual sugars, pH, and flavor development. In big factories, this data is fed into digital brewing systems that model yeast health and fermentation curves. If something's off, brewers are alerted immediately. Once fermentation is complete, the beer isn't quite ready. It must be conditioned, held at near freezing temperatures to clarify and stabilize. During this stage, yeast settles out, flavors mellow, and carbonation levels are adjusted. Some factories use centrifuges to speed clarification. Others rely on time and gravity. Filtration may be employed, either with diatomaceous earth, membranes, or cross-flow systems to remove fine particulates and ensure brilliant clarity. For beers that are meant to be bright and shelf-stable, pasteurization may follow, either flash pasteurization or tunnel pasteurization. But not all beer is pasteurized. Many craft style or draft-only products skip this step to retain delicate aromas. Once the beer is bright, cold, and stable, it's ready for packaging. In large breweries, packaging lines are like choreographed metal highways. Bottling lines can run at 1,200 bottles per minute. Can lines are even faster. Kegs are cleaned, filled, capped, and labeled by machines. Bottles are rinsed, filled under pressure to avoid foaming, sealed with crown caps, and passed through date coders and labelers. Cans are seam locked, rinsed, and pressure checked. Every container is sampled for fill height, oxygen pickup, carbonation, and microbial safety. In some facilities, advanced cameras scan every bottle or can for imperfections in milliseconds. The packaging halls are cold, loud, and almost hypnotic. Conveyor belts twist and curve. Robotic arms stack cases onto pallets. Shrink wrap machines seal entire loads for distribution. Forklifts or automated guided vehicles shuttle product to cold storage, where beer awaits distribution to bars, grocery stores, sports stadiums, and corner shops around the world. But behind the machinery is a deeper layer of quality assurance. Beer is a living product, and even at massive scale, breweries run labs that would rival pharmaceutical facilities. There are microbial labs, sensory panels, gas chromatographs, and mass spectrometers analyzing aroma compounds, esters, sulfur levels, and oxygen ingress. Trained tasters, often called sensory analysts, taste beer daily, blind, and score it against reference samples. A slight change in carbonation or hop aroma is enough to flag a batch for review. And hygiene is non-negotiable. Brewing equipment is cleaned constantly with clean-in-place systems that circulate caustic solutions, acid rinses, and sanitizers through every pipe, pump, tank, and valve. Breweries are designed with sloped floors, airlocks, positive pressure rooms, and filtered ventilation to minimize contamination. Yeast cultures are kept in pure, cryogenically preserved banks and propagated in sterile fermenters. Even the water is treated, filtered, softened, and dechlorinated to ensure it doesn't introduce off flavors. Despite the scale, there's a strange elegance to the whole system. Every tank, pump, sensor, and pipe is part of a carefully designed loop. From raw grain to finished beer, the factory operates almost like an ecosystem, closed, balanced, and tightly monitored. Nothing is left to chance. Even the CO2 released during fermentation is often captured and reused to carbonate the final product, reducing waste and environmental impact. Bicardi all starts with molasses, a byproduct of sugar refining. Once cane juice has been boiled and crystallized into sugar, what remains is a dark, viscous liquid rich in residual sugars and minerals. Bicardi sources its molasses primarily from the Caribbean and Central America, where sugarcane grows in abundance. Shipments arrive by the ton, offloaded into deep storage tanks that keep the molasses warm and pumpable. Its smell is rich and heavy, deeply sweet, slightly sour, with a roasted, almost smoky undertone. Before fermentation begins, the molasses is diluted with pure water and combined with nutrients to prepare what's known as the fermentation wash. Bicardi uses a proprietary strain of yeast, one that's been carefully preserved and propagated for generations. This yeast is key. It's what gives Bicardi its distinctive profile: clean, light, with subtle fruity esters and very low levels of fusel oils. In a dedicated propagation room, yeast cells are grown in increasingly larger vessels, fed on molasses and oxygen, until they're strong enough to handle full-scale fermentation. The prepared wash, diluted molasses, nutrients, and yeast is pumped into fermentation tanks, towering steel vessels the size of small silos. Fermentation is fast and efficient, typically 24 to 30 hours. During that time, the yeast devours the sugars, converting them into alcohol and CO2. The temperature is carefully regulated. Too hot, and the yeast dies. Too cold, and it underperforms. Sensors monitor every parameter in real time: sugar levels, temperature, pH, alcohol content. In massive control rooms, technicians watch digital dashboards as each tank ferments with machine-like consistency. The result of this stage is not rum yet. It's a low alcohol liquid called wash or beer, usually around 7 to 10% ABV. It smells nothing like rum. It's sweet, funky, raw. To transform it into the clear, potent spirit known around the world, Bicardi moves to the next phase: distillation. Distillation is where alcohol is concentrated and flavors are defined. Bicardi doesn't rely on pot stills, as many small batch rums do. Instead, it uses continuous column stills, tall, multi-stage distillation towers that can separate alcohol with incredible precision. These columns have trays or packing materials inside that force the vapor and liquid to interact repeatedly, concentrating the alcohol while removing unwanted compounds. The fermented wash is pumped into the column, heated from the bottom, and as it rises, different components evaporate at different heights. Light, clean alcohols rise to the top and are collected. Heavier compounds are left behind and drained off. By adjusting the temperatures and reflux ratios, Bicardi's distillers control the exact cut of alcohol they want to keep. The result is a high-strength spirit, often 85% ABV or higher, that's clear, light, and extremely pure, essential for Bicardi's signature smoothness. But pure alcohol isn't rum yet. The next steps, aging, blending, and finishing, are where the artistry comes in. The raw distillate, also called aguardiente, is diluted down to around 60 to 70% ABV and pumped into oak barrels for aging. Bicardi primarily uses used American white oak barrels, many of which once held bourbon. These barrels are charred on the inside, and over time, they impart color, vanilla notes, spice, and tannins to the rum. In Bicardi's aging warehouses, massive barrel halls with racks stacked to the ceiling. Tens of thousands of casks rest in the tropical heat. The climate speeds the interaction between spirit and wood, making even short aging periods highly effective. Different rums are aged for different durations. Bicardi Superior, the classic white rum, may be aged for as little as 1 year before being filtered. Gold and flavoured varieties rest longer. Premium products like Bicardi 8 or Bicardi Reserva Limitada are aged 8 to 12 years or more. Each barrel breathes. Alcohol evaporates, a phenomenon known as the angel share, and oxygen seeps in. Over time, harsh edges soften, flavours deepen, and the rum becomes increasingly complex. Once aging is complete, barrels are emptied, and the rum is evaluated. This is where Bicardi's master blenders, trained experts who can detect flavour differences down to the subtlest note, step in. Dozens, sometimes hundreds of barrels are selected and blended together to create a final product with exactly the right profile. Some rums bring fruity notes, others deliver weight or spice, others still provide structure or sweetness. The blender's job is to make the sum better than the parts, and to ensure that every bottle tastes exactly like the last one, year after year. Now comes one of Bicardi's most distinctive processes, charcoal filtration. For Bicardi Superior and other light rums, the blended rum is passed through layers of activated charcoal, often made from coconut husks, to remove colour and certain heavy flavour compounds. This process, inspired by Don Facundo Bicardi himself in the 1860s, strips away rough edges and leaves the rum bright, clean, and smooth. Even after aging in oak, the charcoal returns the rum to a near-clear appearance while preserving its vanilla and almond undertones. Once filtered, the rum is diluted with ultra-pure demineralized water down to bottling strength, usually 37.5% or 40% ABV, depending on the market. It's then passed through fine mesh filters to remove any remaining particles, chilled to encourage clarity, and tested for stability. Quality checks are constant. ABV, color, turbidity, aroma, flavor, all are measured in both labs and sensory rooms. Finally, the rum is ready to be bottled. Bicardi's bottling lines are massive, high-speed operations, capable of producing tens of thousands of bottles per hour. Empty glass bottles, custom-shaped with embossed bats and logos, are automatically loaded onto conveyors. They're rinsed, filled with rum under pressure, sealed with tamper-proof caps, and labelled with laser precision. Date codes are printed, barcodes are verified. Every bottle passes through inspection tunnels equipped with cameras and sensors to catch defects, underfills, or misplaced labels. From there, bottles are packed into cartons by robotic arms and shrink-wrapped onto pallets. Pallets are barcoded, logged, and stacked in warehouse zones ready for distribution. Bicardi's logistics network spans continents. From a single facility, trucks, ships, and containers move product across the globe to supermarkets in Spain, beach bars in Brazil, nightclubs in New York, and resorts in Thailand. Behind the scenes, sustainability plays an increasing role. Many of Bicardi's distilleries use renewable energy, recycle processed water, and recover CO2 from fermentation. Spent yeast and distillation byproducts are often converted into animal feed or used in bioenergy systems. Even the barrels, when retired, may be repurposed for furniture, flooring, or smaller barrel aging projects. Waste reduction is not just about economics. It's part of preserving the legacy of the land and the product itself. And yet, for all this technology and scale, Bicardi's rum still carries with it a certain history, a sense of origin. The company was founded in 1862. and though exiled from Cuba in the 1960s, its roots remain in the tropics. The smoothness of Bicardi rum isn't just a technical achievement, it's a philosophy. Every step, from selecting molasses to filtering the final spirit, is guided by an obsession with drinkability. A Bicardi rum should be mixable, approachable, and endlessly clean on the palate. Jack Daniel's begins with a precisely controlled mash bill of 80% corn, 12% malted barley, and 8% rye. The grains arrive in massive quantities by rail and truck and are stored in silos before being milled on-site in Lynchburg, Tennessee. Corn is cracked into coarse grits. Malted barley and rye are milled finer. The grain is moved pneumatically into huge stainless steel cookers where it undergoes a staged cooking process. Corn first, cooked at a high temperature to gelatinize the starches, then rye, then finally malted barley is added as the mash cools to around 65 degrees Celsius. The malt's enzymes convert starches into fermentable sugars. The resulting mash is pumped into one of 64 fermentation vats, open-top tanks made from cypress wood, some more than 80 years old. These vats each hold around 40,000 gallons. Jack Daniel's uses its own proprietary yeast strain, maintained and propagated internally since the early 20th century. Before yeast is pitched, a portion of the previous day's fermented mash is added to the new batch. This sour mash technique helps control the pH and microbial stability of the fermentation environment. Yeast is pitched in liquid form and begins consuming sugars, producing ethanol and CO2. Fermentation lasts 4 to 6 days. The mash foams, bubbles, and gives off heat. During peak fermentation, tanks require constant monitoring for overflow and contamination. Automated sensors track sugar depletion, CO2 output, and temperature curves. Staff monitor the aroma, foam height, and microbial activity daily. When fermentation is complete, the liquid contains roughly 7-9% alcohol by volume. This distiller's beer is pumped into column stills, massive stainless steel and copper columns more than 40 feet tall. Jack Daniel's uses a single-stage continuous distillation process. Beer enters the column at various levels, while steam is injected from below. Alcohol vapor rises, separating from heavier components. The alcohol vapor is routed to a doubler, essentially a pot still operating at atmospheric pressure, where it's condensed, reheated, and distilled again. The resulting clear spirit, often referred to as white dog, emerges at around 140 proof. Before aging, Jack Daniel's performs its most defining step, the Lincoln County process, or charcoal mellowing. This process takes place in vats over 10 feet tall, filled with sugar maple charcoal. The charcoal is made on-site by stacking 2x 2-inch thick maple planks into long rows, igniting them with high-proof whiskey and letting them smolder until fully carbonized. Once cooled, the charcoal is ground into chunks and loaded into mellowing vats. The white dog is slowly trickled, drip by drip, through 10 feet of charcoal, taking 4 to 5 days to pass completely through. The charcoal removes fusel oils, aldehydes, and other harsh flavor compounds. The process is gravity-fed and unpressurized, requiring a consistent flow rate to maintain quality. The resulting spirit retains its proof, but emerges smoother and cleaner, with noticeably reduced volatility. Once mellowed, the whiskey is moved into new, charred American white oak barrels, coopered at Jack Daniel's own barrel-making facility. The staves are air-seasoned outdoors for 6 months to 2 years, then assembled, toasted, and flame-charred to a specific level designed to maximize flavor extraction and color development. Each barrel holds about 53 gallons. The inside is blackened from charring, and the wood sugars have caramelized. Barrels are filled at 125 proof and rolled into one of 90-plus barrel houses across the Lynchburg area. These rickhouses vary in size and construction. Some are multi-story wood frame structures, others are steel-clad, but all use passive temperature variation to promote aging. Inside the barrel house, environmental conditions vary dramatically. Upper floors reach 100 degree F+ in summer, encouraging evaporation and faster aging. Lower levels remain cooler and more stable. Jack Daniel's does not rotate barrels between floors, so aging is not uniform. Instead, blending later equalizes the flavor profiles. Barrels are stacked on wooden ricks, often 6 to 7 high. During aging, the whiskey interacts with the wood. Alcohol penetrates the staves, extracting vanillin, lignin-derived compounds, tannins, and hemicellulose breakdown products like caramelized sugars. Oxidation occurs gradually as oxygen seeps through the porous wood. Angel's share evaporation causes the proof to rise over time and concentrates the flavor. Each year, a barrel loses 5% of its volume to evaporation. Maturation time varies by product. Old No. 7 typically ages for 4 to 6 years. Higher-end expressions like Single Barrel or Sinatra Select may rest for up to 8 years or more. Throughout aging, barrels are sampled periodically. Staff draw whiskey using a thief and assess it by color, aroma, proof, and mouthfeel. No age statement is printed on standard Jack Daniel's because blending is used to maintain consistency, not target a specific age. When deemed mature, barrels are dumped onto a stainless steel trough, filtered through mesh screens to catch char, and moved to batching tanks. Here, up to 200 barrels are blended into a single batch. Before bottling, the whiskey is chill filtered, cooled to near freezing, and passed through paper or cellulose filters to remove fatty acid esters that can cause clouding in the bottle. For Old No. 7, the spirit is then diluted to 80 proof, using demineralized water drawn from the same cave spring used for mashing. Other products, like bonded or single barrel proof, may be bottled at higher strengths or without filtration, depending on the release. Bottling takes place on high-speed automated lines. Empty bottles are rinsed with pressurized air or filtered water. Filling machines dispense whiskey using gravity-fed nozzles or vacuum-assisted pumps. Bottles are capped with aluminum closures, corks, or synthetic caps depending on the SKU. Labels are applied using roll-fed labelers with electronic eyes that verify positioning. Lot codes and production dates are printed in UV ink or laser etched onto the neck. Every bottle passes under fill level sensors and automated cameras. Defective units are ejected immediately. Bottles are grouped into cases, shrink-wrapped, and palletized by robotic arms. Finished goods are transported to climate-controlled warehouses. Logistics teams track SKU distribution globally. Jack Daniel's is shipped to more than 170 countries. Each batch must meet regional regulatory standards. Export whiskey may require separate bottling or labeling runs to comply with EU, UK, or Asian labeling laws. Quality control labs sample bottles from each run and perform gas chromatography and spectrophotometry to confirm chemical composition. Sensory analysts run blind tastings daily to validate flavor accuracy. Any deviation from the flavor profile, too much wood, too much sweetness, excessive ethanol burn, results in a hold or rework. Spent grain from mashing is pumped to presses, dried, and sold as cattle feed. Wastewater is treated on-site using anaerobic digesters and aerobic ponds before being discharged or reused. Energy recovery systems capture steam from cooking and distillation to heat water for fermentation tanks. Charcoal from the mellowing vats is replaced regularly and either regenerated or disposed of as biomass fuel. Spent barrels are sold to Scotch distilleries, hot sauce producers, and breweries for secondary use. The cooperage also reconditions barrels for use in cask-finished products or special editions. The distillery operates under strict federal and state regulation. Every barrel and bottle is tracked with a unique serial number. auditors inspect warehouse records, bottling logs, and inventory counts. The distillery maintains TTB-compliant records for every production step, from raw grain receipt to final export certificate. Barcodes and RFID tags on pallets ensure traceability from distillation to retail shelf. Security is tight, bonded warehouses are sealed, and access is controlled. Jack Daniel's uses SAP-based systems for production scheduling, batch tracking, and global inventory management. Brewing, fermentation, and distillation data are logged automatically by PLCs connected to SCADA systems. Operators monitor process parameters in real time on touchscreen interfaces. Alerts are triggered if mash temperature, fermenter pressure, still output, or bottling line speed moves out of range. Scheduled maintenance is performed weekly. Sensors check flow rates, valve positions, CIP cycle effectiveness, and tank volumes continuously. Yeast propagation is handled in a sterile lab with HEPA-filtered air, jacketed tanks, and strict aseptic technique. Each batch of yeast is cryogenically preserved and banked in long-term storage. Lab staff test yeast for viability, contamination, and fermentation performance. Infection events, such as wild yeast or lactic acid bacteria, are rare but can halt production for full CIP sanitization of all affected equipment. Sanitizers include caustic soda, peracetic acid, and steam. Safety inspections and confined space protocols are rigorously enforced, especially around fermentation tanks, high-pressure steam lines, and ethanol vapor zones. Mash cookers and fermentation tanks are cleaned between every batch. Distillation columns are stripped and acid washed quarterly. Mellowing vats are emptied and replenished every few months. Barrels are inspected for leaks before filling. Leakers are flagged and re-co-opted or discarded. Every floor drain, gasket, and pump seal is part of a scheduled inspection checklist. The entire facility is USDA certified for food safety and operates under HACCP protocols. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. CAFE practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under CAFE practices, the beans are harvested, typically by hand. Hand picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill seal systems for smaller bags and horizontal form fill seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers, such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin, are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 litres. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill-seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch, while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. The Canada Dry production process begins with the intake and treatment of raw water. Municipal water is directed into a series of pre-treatment systems through stainless steel pipelines. The first step is mechanical filtration, where water flows through mesh strainers that remove coarse particulates. Following this, it passes through a dual media sand and anthracite filtration system to eliminate finer suspended solids. The next stage is activated carbon filtration. As the water moves slowly through the carbon beds, chlorine, chloramine, and organic contaminants are removed through adsorption. The water is then softened using a sodium-based ion exchange system that exchanges calcium and magnesium ions for sodium ions, reducing scale formation in downstream equipment. After softening, the water is subjected to reverse osmosis using high-pressure pumps to force it through semi-permeable membranes that separate out dissolved solids, bacteria, and unwanted ions. The treated water then undergoes ultraviolet sterilization and sub-micron filtration to achieve microbiological purity before being transferred to agitated, sealed stainless steel storage tanks for use in the product blend. Parallel to this, the syrup production begins in a closed system syrup room. Liquid sweeteners, such as high fructose corn syrup, are delivered in heated tankers and pumped into bulk storage silos lined with food-grade coatings. These silos are equipped with volumetric flow meters and thermal controls. The sweetener is metered into stainless steel mixing vessels using precision dosing pumps. These vessels are jacketed for thermal regulation and include bottom-mounted mixers driven by variable frequency motors to achieve high shear mixing. Ginger extract, lime oil, lemon oil, and proprietary spice emulsions are stored in temperature-controlled dosing cabinets and delivered via sealed piping to the blending tanks. Dosage is governed by recipe management software, with peristaltic pumps calibrated for microdosing accuracy. Citric acid is introduced to provide tartness, followed by potassium sorbate or sodium benzoate as preservatives. Caramel color, if used, is injected through positive displacement pumps, controlled to a fraction of a milliliter per liter. Once all components are in the tank, the syrup undergoes a high shear mixing cycle. After homogenization, it is flash pasteurized by pumping through a plate heat exchanger system, reaching temperatures above 85 Stevnik for a few seconds, and then rapidly cooled using a countercurrent chilling loop. The syrup is passed through sterile filters and transferred into insulated holding tanks with nitrogen blankets to prevent oxidation and maintain flavor integrity. With syrup and water prepared, they are combined using an inline blending system. This unit uses magnetically driven flow meters to monitor real-time volumetric flow of each stream. PID-controlled valves adjust the ratio continuously to maintain the programmed syrup-to-water proportion. The blend passes through a series of mixing chambers where turbulence is created using static mixers to ensure full molecular integration. An inline refractometer measures the resulting Brix level, and adjustments are made automatically to ensure target sweetness is met within plus 0.1 Brix. After blending, the mixture is deaerated in a vacuum vessel. Liquid enters a chamber under reduced pressure, causing entrained oxygen and other gases to escape. The deaerated product is immediately cooled through a glycol-based plate chiller to a temperature just above 0 degrees, maximizing carbon dioxide solubility in the next step. The cold, deaerated blend is sent to the carbonation module. Here, liquid CO2 is introduced into the beverage via high-precision sparging rings located at the base of the carbonation tank. The tank operates under constant high pressure and uses recirculation pumps to keep the liquid moving over the gas interface, improving dissolution rates. Carbonation levels are controlled through feedback loops tied to gas volume analyzers that measure dissolved CO2 in real time. Once carbonated, the product is routed through pressurized transfer lines to filling buffer tanks. These tanks maintain positive pressure to prevent gas loss and are fitted with level sensors and pressure regulators. Container preparation runs in parallel. Empty aluminum cans or PET bottles are delivered via automated depalletizers that use vacuum pads or mechanical sweep arms to remove layers of containers and place them on conveyor systems. The containers pass through a cleaning unit where they are inverted and rinsed internally with filtered, ionized air or sterile water. Any residual moisture is blown off using high-velocity air knives. Clean containers proceed to the filling carousel. The filling system consists of a rotary filling machine with 60 to 120 heads, depending on capacity. Each container is raised into position against a filling valve. The system first applies counterpressure to match internal carbonation levels and prevent foaming. Filling valves open when pressure equalization is achieved. Product flows into the container through gravity or gentle pressurization. During fill, displaced gas vents through a return tube to maintain equilibrium. Fill volume is controlled by valve timing or volumetric flow measurement. Once filled, the valve closes and the container is lowered back to the conveyor. Capping occurs immediately after filling. For bottles, closures are delivered by an oriented cap feeder using centrifugal force. Caps are guided into a chute and pressed onto bottles by servo-controlled capping heads with adjustable torque settings. For cans, aluminum ends are fed into place from a lid magazine. A seamer head performs a double-fold operation, curling the lid's flange over the rim of the can and compressing the metal layers together to form an airtight seal. Sensors verify each seal, and containers with improper application are ejected from the line. Filled and sealed containers are conveyed through a vision inspection system equipped with high-speed cameras and LED backlighting. Algorithms analyze fill height, cap placement, and label orientation. Infrared sensors check for proper internal pressure via deformation profiles. Containers that do not meet specification are removed from the line using pneumatic pushers. Labeling systems vary by format. PET bottles pass through wraparound labelers that apply pressure-sensitive or roll-fed film labels. Servo motors control label placement, while rubber rollers press labels onto the surface. Cans use shrink sleeve applicators, where sleeves are dropped over the container body and pass through a heat tunnel. The tunnel uses either infrared or steam heat to contract the film evenly around the can. Label inspection units verify barcode readability, positioning, and design accuracy. The finished containers are then grouped into multi-packs. Bottles are sorted and arranged into clusters using pneumatic sweep arms and placed into molded plastic carriers or corrugated trays. Cans are conveyed into shrink wrapping units, where sets of 6, 12, or 24 are collated onto a moving belt. Polyethylene shrink film is dispensed over the groups and sealed at the edges. The packages move through a heated tunnel with recirculated hot air that shrinks the film tightly around the cans, securing them in a stable bundle. Multi-packs advance to the case packing area. Automatic case erectors unfold corrugated blanks into boxes and place them on a conveyor. Robotic gantries fitted with suction grippers pick up multiple multi-packs at once and lower them into open cases. Depending on format, cases may be closed using tape applicators or hot melt glue systems. Completed cases are scanned for contents, weight, and closure integrity using inline check weighers and vision systems. Palletizing begins with pallet dispensing. Wooden or plastic pallets are fed from a vertical stack onto a chain conveyor. Robotic palletizers, equipped with multi-axis arms, arrange cases on the pallet in interlocking patterns to maximize stability. Slip sheets may be inserted between layers using vacuum pick-and-place units. Once stacking is complete, the pallet moves into an automatic stretch wrapper. Here, the pallet is spun on a turntable while a film carriage applies tensioned polyethylene film around the load. The film is heat-sealed at the end of the cycle, and the wrapped pallet is discharged to a staging conveyor.